Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring one of nature's most beautiful and enchanting phenomena, the rainbow. A bridge of color that appears after storms, a promise painted across the sky, and a wonder that has captivated humanity since the beginning of time. Rainbows are fleeting visitors, arriving without warning and departing just as quickly. Yet, in their brief appearance, they transform ordinary moments into something magical. Above us, when conditions align perfectly, water and light collaborate to paint arcs of pure color across the heavens. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the gentle colors of the rainbow to carry you into peaceful sleep. Let's begin. The nature of light and color. Every rainbow begins with sunlight, though you might not realize it at first. Sunlight appears white to our eyes, a single beam illuminating the world around us. But hidden within that whiteness is a spectrum of colors, each one traveling at a slightly different wavelength through space. Red, orange, yellow, green, blue, indigo, and violet, all woven together so seamlessly that we cannot tell them apart until something separates them. That something is often a raindrop, a tiny sphere of water suspended in the air, waiting to catch the light. When sunlight enters a raindrop, it bends. This bending is called refraction, and it happens because light travels at different speeds through different materials. In air, light moves quickly, racing at nearly 300,000 kilometers per second. In water, it slows down just enough to change direction, creating the magic that leads to rainbows. As the light passes through the raindrop, it spreads into its component colors like a prism unwrapping a gift that was always there but hidden from view. Each color bends at a slightly different angle because each wavelength interacts with water uniquely. Red bends the least, violet bends the most, and all the colors in between find their places along the spectrum. Inside the raindrop, the light bounces off the back surface like a mirror, reflecting toward the front again. When it exits the raindrop, it bends once more, separating even further into distinct beams of color. What emerges is not white light, but a fan of colors, each one traveling in a slightly different direction through the air. Millions of raindrops do this simultaneously, each one sending its own spectrum of light toward your eyes from slightly different positions in the sky. The result is a rainbow, an arc of pure color suspended in the atmosphere, shimmering between earth and cloud. The process is so precise, so delicate, that even the slightest change in conditions can alter or erase the rainbow entirely. A shift in the angle of sunlight, a change in droplet size, or a movement in your position, and the rainbow transforms or disappears. Yet when everything aligns perfectly, when the sun shines from behind you and rain falls in front of you at just the right distance, nature performs this gentle magic without effort or intention. To understand a rainbow is to understand light itself, traveling through space, bending at boundaries, reflecting from surfaces, and revealing the hidden colors it carries within its seemingly simple white beam. Each rainbow is a reminder that beauty often hides in plain sight, waiting for the right moment to show itself. The same sunlight that warms your face and lights your day contains all these colors always, and the rainbow simply makes visible what was invisible before. Why rainbows are arcs? Rainbows always appear as arcs, curving gracefully across the sky, in a perfect mathematical shape. This form is not random or artistic, but mathematical and precise, determined by the angle at which light exits the raindrops after its journey of refraction and reflection. When sunlight enters a raindrop, reflects inside, and exits again, it does so at a specific angle, approximately 42 degrees from the line between the sun and your eye. This angle is consistent for every raindrop involved in creating your rainbow, creating a cone of light with your eye at the very tip of that cone. You see this cone as a circle when viewed from the right perspective, but because the ground blocks the lower half, cutting off the bottom portion of that circle, it appears to us as an arc stretching across the sky. If you were high enough, perhaps in an airplane cruising above the clouds or standing on a mountaintop with mist swirling below you in the valley, you might see the full circle of a rainbow, an unbroken ring of color surrounding the shadow of your aircraft or your own head, projected onto the clouds beneath. This complete circular rainbow is sometimes called a glory, and it proves that rainbows are not actually arcs at all, but circles that we simply cannot see in their entirety from our usual vantage point on the ground. The arc's perfect curve comes from geometry and physics working together in harmony. Each color has its own specific angle of refraction, with red appearing at the outermost edge at about 42 degrees and violet at the innermost edge at about 40 degrees. The radius of the arc never changes, no matter where you stand or how large the rainbow appears to be in the sky. Move closer to the rain, and the rainbow moves with you, maintaining that 42-degree angle. Walk backward away from the rain, and it follows, never allowing you to approach it or touch it. You can never reach a rainbow's end because it exists only as a relationship between sunlight, water droplets, and your eyes. It is not a physical object you can walk to or touch, but an optical phenomenon, a collaboration between nature and perception that requires your presence as the observer. The arc reminds us that rainbows are deeply personal experiences. Two people standing side by side, even just a meter apart, see slightly different rainbows, each created by different raindrops scattering light at the precise angle needed to reach their individual eyes at their specific positions. Your rainbow is yours alone, painted just for you by the alignment of sun and rain and vision. This makes every rainbow a private showing, a unique moment of beauty that belongs to the observer and no one else, existing only in the relationship between the viewer and the elements. The colors always appear in the same order. Red always rests on the outside of a rainbow's arc, followed by orange, then yellow, then green, then blue, then indigo, and finally violet, curving along the innermost edge. This order never changes, and it cannot change, because it is determined by the fundamental wavelengths of light itself, built into the very nature of electromagnetic radiation. Red light has the longest wavelength visible to human eyes, measuring about 700 nanometers from crest to crest as it travels through space. Because of this longer wavelength, red bends the least when passing through water, refracting at a larger angle and appearing on the outside of the arc. Violet has the shortest wavelength that we can see, around 400 nanometers, and it bends the most when entering and exiting water, placing it on the inside of the rainbow's curve. The other colors arrange themselves in between according to their wavelengths, each finding its place in the spectrum according to the laws of physics. This consistent sequence gave rise to many memory aids over the centuries, tools to help people remember the order of colors. ROYG, BIV, a name constructed from the first letters of each color, helps students and skywatchers remember the progression from outer to inner. Red, orange, yellow, green, blue, indigo, violet. Some people prefer other mnemonics, creating sentences where each word begins with the appropriate letter, turning the physics of light into memorable phrases. The boundaries between colors are not sharp lines, but gradual transitions, smooth gradients where one hue fades imperceptibly into the next. Red fades into orange without a clear dividing line, orange into yellow, each color blending with its neighbors like watercolors on wet paper, creating infinite subtle shades between the named colors. Our eyes perceive these as distinct bands only because our brains categorize the continuous spectrum into separate hues, dividing the infinite gradient into manageable categories. In reality, a rainbow contains every shade between pure red and pure violet, an infinite number of colors compressed into a luminous arc spanning the sky. Some cultures recognize more than 7 colors in a rainbow, dividing the spectrum more finely, while others see fewer, combining what we might call separate colors into single categories. This proves that the divisions are as much cultural as they are optical, shaped by language and tradition. Regardless of how we name them or how many categories we create, the colors remain faithful to their wavelengths, always appearing in the same physical order. A rainbow seen in ancient Mesopotamia displayed the same sequence as one seen today in Tokyo or New York or Cairo. The physics has not changed in thousands of years, and it will not change in thousands more. Red on the outside, violet on the inside, with all the warmth and coolness of the spectrum stretched between them in eternal order. This constancy makes rainbows feel timeless, a phenomenon that has looked the same to every human eye that has ever gazed upon one throughout all of history. Double rainbows tell a story of reflection. Sometimes, if you are fortunate and the conditions are especially favorable, you will see not one rainbow but 2, stacked one above the other in the sky. The second rainbow appears fainter and higher in the sky than the primary arc, with its colors reversed in a mirror image of the first. This is a double rainbow, and it forms when sunlight reflects twice inside raindrops instead of once, taking a longer and more complex path through the water. The extra reflection requires the light to travel a longer distance within each droplet, which is why the secondary rainbow appears dimmer than the primary. More light escapes the raindrop during this extended journey before completing the second reflection, leaving less light to reach your eyes and create the arc. The reversed colors are a direct consequence of this geometry. The second internal reflection sends the light out at a different angle, approximately 51 degrees instead of 42 degrees, and this different angle flips the order so that violet appears on the outside of the secondary bow and red on the inside, the opposite of the primary rainbow below it. Between the two rainbows lies a darker band of sky called Alexander's Band, named after Alexander of Aphrodisias, a Greek philosopher who first described this phenomenon in ancient times around 2,000 years ago. This region appears noticeably darker than the sky, both inside the primary rainbow and outside the secondary rainbow, because the angles of reflection do not direct light from either rainbow into this space between them. It is a shadow zone, a quiet interval between two displays of color, where less scattered light reaches your eyes. Observers often describe double rainbows as magical or supernatural, and they are right to feel that way. The conditions must be even more precise for a secondary rainbow to form than for a primary rainbow. The rain must be heavy enough to provide sufficient water droplets, the sunlight bright enough to survive 2 internal reflections, and the observer positioned just right to see both arcs simultaneously. When all these factors align perfectly, nature offers a bonus, a second arc, echoing the first, framing the sky with doubled beauty. Triple and even quadruple rainbows are theoretically possible, formed by 3 or 4 internal reflections within the raindrops, but they are exceedingly rare and difficult to see with the naked eye. Each additional reflection weakens the light exponentially, rendering these higher-order rainbows almost invisible against the brightness of the sky. The third-order rainbow would appear on the same side of the sky as the sun, around 40 degrees away from it, making it nearly impossible to see due to the sun's overwhelming brightness. Photographs taken with careful positioning and long exposures have captured these elusive higher-order rainbows under ideal conditions. But to the naked eye, during casual observation, they remain invisible whispers of color, barely distinguishable from the background sky. Double rainbows, however, are common enough that most people will see one at some point in their lives if they watch the sky regularly after storms. A reminder that nature's generosity sometimes exceeds our expectations, offering more beauty than we dared to hope for. Rainbows appear only when the sun is behind you. To see a rainbow, you must stand with your back to the sun and face the rain or mist. This rule is absolute and unchanging, determined by the fundamental geometry of light refraction and reflection. If you face the sun, the rainbow will form behind you, invisible and unreachable, painting colors in the sky where you cannot see them. The anti-solar point, the spot directly opposite the sun from your perspective, becomes the center of the rainbow's circular arc. The lower the sun sits in the sky, the higher the rainbow rises above the horizon. At sunset or sunrise, when the sun hovers near the horizon at its lowest point in its daily arc, rainbows can arch magnificently high into the sky, sometimes spanning vast portions of the visible heavens from one horizon to the other. Midday rainbows are rare and low because the sun's high angle in the middle of the day limits how much of the arc can appear above the horizon. And when the sun rises higher than 42 degrees, rainbows become impossible to see because the entire circular arc would be below the horizon. This dependence on sun position explains why rainbows appear most often in late afternoon, especially in temperate regions where weather systems typically move from west to east. After storms pass through during the day, the sun breaks through the clouds from the west, while rain lingers in the eastern sky. Standing between them, you become the essential fulcrum of color, the necessary observer completing the optical triangle of sun, rain, and sight. Morning rainbows are equally beautiful, but require rain in the west and sun in the east, a less common arrangement in many climates, where prevailing winds and weather patterns favor afternoon appearances. Tropical regions, where brief showers punctuate sunny days throughout the day, offer more frequent opportunities for rainbows at various times than temperate zones, where weather systems are broader, slower moving, and more persistent. The requirement for sun behind and rain ahead makes rainbow chasing a matter of positioning and awareness. If you see rain approaching from one direction while the sun shines, you know to turn your back to the sun and face the rain, then wait and watch. If the sun emerges behind you after a storm has passed through, you immediately turn to face the departing clouds in the opposite direction, scanning for the telltale arc of colors. This predictability removes none of the wonder or magic, but it does give us a sense of control and understanding, a way to anticipate and seek out these moments of beauty, rather than waiting for chance alone to deliver them. Knowing where to look transforms you from passive observer to active seeker, someone who reads the sky's conditions and positions themselves accordingly. Rainbows last only as long as the rain and sun coexist. A rainbow's life is brief and fleeting, lasting only as long as sunlight and water droplets occupy the air together in the right configuration. When the rain stops, the droplets fall to the ground or evaporate into invisible vapor, and the rainbow fades from view as the screen of water that creates it disappears. When clouds cover the sun, blocking its light, the light source vanishes, and the colors disappear instantly, as though someone turned off a switch. This fleeting nature makes rainbows feel precious, gifts of perfect timing that cannot be grasped, captured, or held. You cannot bottle a rainbow or preserve it for later viewing. It exists in the present moment, then dissolves back into ordinary air and light, leaving only memory and perhaps photographs behind. Ancient peoples must have marveled at this impermanence, watching colors bloom brilliantly and then wither in minutes, appearing and disappearing like magic. Some rainbows last only seconds, visible for a single heartbeat, before conditions shift and they vanish as if they never existed. A gap in the clouds allows sunlight through for just a moment, creating a brief arc before closing again. Others linger for 20 minutes or more, glowing steadily as rain showers drift slowly across the landscape while the sun continues to shine. The longest-lasting rainbows occur when weather systems move slowly, maintaining the delicate balance of sun and rain for extended periods. Slow-moving frontal systems or stationary showers can keep conditions stable, allowing the rainbow to persist as a nearly constant feature of the sky. But even these eventually fade, replaced by clear skies as the rain ends or by darkness as the sun sets. The transience of rainbows mirrors many beautiful things in life. Sunsets that paint the sky for minutes before darkness falls, shooting stars that streak and vanish, blooming flowers that unfold and wilt. They remind us that some experiences cannot be captured or controlled, only witnessed and remembered, existing fully only in the present moment. This ephemerality may actually be a fundamental part of their appeal to human observers. If rainbows were permanent fixtures in the sky, always visible like mountains or stars, would we treasure them as much? Would we stop and stare? Or would we ignore them as we ignore so much of our everyday environment? Their rarity makes each sighting feel like a small miracle, a convergence of circumstances that might not happen again for days or weeks or even months. When you see a rainbow, you are seeing something that did not exist moments before and will not exist moments after. It is a performance with no rehearsal and no encore, offered once to those who happen to be watching and then withdrawn forever. To stand in its presence is to participate in something unrepeatable and unique, a moment that belongs only to you and to those who share it with you in that place and time. Moonlight can create rainbows. Two rainbows are not exclusive to daylight hours and bright sunshine. On rare occasions, when the moon is bright and full, hanging high in a clear night sky, and rain falls through the darkness, lunar rainbows appear. Also called moonbows or night rainbows, these spectral arcs are much fainter than their solar counterparts because moonlight is merely reflected sunlight, far dimmer than the direct beams of day, perhaps 100,000 times less intense. To human eyes adapted to darkness, moonbows often appear almost colorless, glowing white or pale gray against the dark sky, rather than showing the vivid spectrum we expect from daytime rainbows. Our eyes rely on two types of photoreceptor cells: cones for color vision in bright light, and rods for low light vision in darkness. In the dim light of a moonbow, the rods dominate our vision, and they cannot distinguish colors well because they lack the color-sensitive pigments found in cones. The rainbow is there, complete with its full spectrum of colors, but our night-adapted vision cannot perceive it fully, seeing mainly shades of gray instead. Cameras, however, can capture the colors that our eyes miss in the darkness. Long exposure photographs reveal moonbows in full color, showing red and violet and everything between, proving that the phenomenon is physically identical to daytime rainbows, except for the intensity of the light source. The same physics applies, the same angles, the same refraction and reflection, just with weaker illumination that our eyes struggle to process in full color. Waterfalls are excellent places to see moonbows because they generate constant mist, providing the water droplets needed even when rain is absent from the sky. Yosemite Falls in California, Victoria Falls on the border of Zambia and Zimbabwe, and Cumberland Falls in Kentucky are famous for their lunar rainbows, drawing visitors who carefully time their trips to coincide with full moons and clear skies, planning their visits months in advance. Indigenous cultures around the world have stories about moonbows, often treating them as more mystical or supernatural than solar rainbows. Their rarity and ghostly appearance lend them an otherworldly quality that inspired myths and legends. In some traditions, moonbows are seen as bridges for spirits or pathways between worlds, liminal phenomena that exist in the boundary between day and night. To stand beneath a moonbow is to experience the night sky in a new way, where darkness is punctuated not by stars alone, but by arcs of hidden color, visible yet invisible simultaneously. The phenomenon reminds us that beauty does not rest when the sun sets. It simply changes form, becoming quieter and more subtle, waiting patiently for those patient enough to seek it in the darkness and willing to let their eyes adapt to perceive it. Some rainbows form without rain. Not all rainbows require rain falling from clouds above. Any time sunlight encounters water droplets suspended in air, whether from weather or from human activity, a rainbow can form if the geometry is correct. The spray from a garden hose, the mist above a waterfall, the fine droplets rising from ocean waves breaking against rocks, the spray from a fountain in a park, all can create rainbows if the angle between sun, water, and observer is right. These smaller rainbows follow exactly the same physical rules as their larger storm-born cousins, bending light at 42 degrees and displaying the same spectrum of colors in the same unchanging order. Children discover this delight on summer afternoons, waving a hose toward the sun and summoning tiny arcs that dance in the spray, creating their own personal rainbows through play and experimentation. The magic is the same whether the water comes from distant clouds or from faucets connected to municipal water supplies. Waterfalls are particularly reliable rainbow generators, among the most dependable places on Earth to see these colorful arcs. The constant cascade throws droplets into the air, creating a permanent mist that catches sunlight throughout the day as the sun moves across the sky. As the sun changes position from morning to afternoon, the rainbow moves too, shifting its location in the mist, but never disappearing entirely, as long as light and water coexist. Niagara Falls on the border between the United States and Canada, Iguazu Falls between Argentina and Brazil, and countless smaller cascades around the world offer nearly guaranteed rainbows to visitors who arrive during sunny weather. The combination of natural grandeur, the roar of falling water, and optical beauty makes these places feel enchanted, as though the landscape itself is performing for those who come to witness. Fountains in city parks can produce rainbows on sunny days, small arcs flickering in and out of existence as the water jets cycle through their programmed patterns. Even the mist from breaking waves at the beach can create fleeting bows if you stand at the right angle relative to the sun, watching the spray catch light as waves crash against rocks or shore. These everyday rainbows lack the dramatic sweep and grand scale of storm-born arcs that span from horizon to horizon, but they carry the same physics and create the same joy in those who notice them. They prove that wonder is not always a matter of scale or grandeur. Sometimes the smallest moments, the light-catching spray from a hose or a fountain, contain the same fundamental beauty as the grandest natural displays, physics and light working together regardless of context. Fog bows appear white and ghostly. When fog replaces rain as the source of water droplets, a different kind of rainbow emerges from the mist. Fog is composed of water droplets far tinier than raindrops, often 100 times smaller or more, microscopic spheres suspended in air. These droplets still refract and reflect light according to the same physical principles, but their small size fundamentally changes the outcome of these interactions. Instead of separating cleanly into distinct colors that spread across the sky, the light from countless tiny droplets overlaps and blends together through a process called interference, producing a white or pale gray arc called a fogbow, also known as cloud bows, when seen from airplanes looking down at clouds below, or as white rainbows by some observers. These ghostly arcs have the same circular shape as colorful rainbows, but lack the vibrant hues we typically associate with the phenomenon. Sometimes faint hints of color appear at the edges of a fogbow, pale reds on the outer rim or blues on the inner edge, but mostly fogbows glow with a soft, ethereal whiteness that seems almost supernatural. Fogbows often appear early in the morning, when mist lingers in valleys or hovers over fields as the sun rises. Hikers in mountains encounter them frequently during their treks, sudden arcs materializing in the fog around them, sometimes surrounding them with rings of pale light that seem to follow as they walk. The effect is surreal and dreamlike, almost disorienting, as though the landscape has become a watercolor painting where all the pigments have run together into white. Because the droplets are so small and numerous, fogbows can be broader and more diffuse than regular rainbows, lacking the sharp definition of a rain-formed arc. They seem to glow from within the fog rather than appearing as a distinct arc separate from it, making them sometimes difficult to photograph clearly. The principle behind fogbows is fundamentally the same as rainbows: light bending and reflecting through water suspended in air. But the size of the droplets determines whether that light emerges as a separated spectrum or as a blended whole. When droplets are large, around 1 millimeter or more, the different wavelengths separate cleanly and produce distinct colors. When droplets shrink below about 1/10 of a millimeter, the waves of different colors interfere with each other, their paths overlapping so much that they combine back into white light. This phenomenon reminds us that nature's laws are consistent, even when the results vary dramatically. Fog and rain are both water, yet they create different expressions of the same underlying physics. Fogbows may not have the drama or vivid beauty of rainbows, but their subtlety holds its own quiet beauty. A whisper where rainbows shout, a gentle presence where rainbows boldly announce themselves. Red rainbows appear at sunrise and sunset. When the sun sits very low on the horizon, either at sunrise just after dawn breaks or at sunset as day fades, its light travels through far more of Earth's atmosphere before reaching the rain that creates the rainbow. This long journey, passing through perhaps hundreds of kilometers of air rather than the shorter path when the sun is higher, gradually filters out the shorter wavelengths of light through a process called Rayleigh scattering. The blues and greens and violets scatter away in all directions, bouncing off air molecules and spreading across the sky, which is why the sky appears blue during the day. What remains after this long atmospheric journey are the longer wavelengths that scatter less easily: red, orange, and yellow. The result is a red rainbow, an arc glowing with warm, fiery colors, rather than the full spectrum we typically see. These red rainbows appear against the deep blues and purples of storm clouds still present after sunset or before sunrise, creating dramatic contrasts that seem almost too vivid to be real. Red rainbows evoke strong emotions in those fortunate enough to witness them. The warm tones, combined with the often dramatic lighting of dawn or dusk, create scenes that feel almost supernatural or otherworldly, as though the normal rules of appearance have been suspended. Photographers cherish these moments above almost any other rainbow sighting, racing against fading light to capture images that seem almost too vivid to be real, checking their camera settings frantically as the light changes by the second. The phenomenon is rare, not because the physics is different from other rainbows, but because the timing must be absolutely exquisite. The sun must be within a degree or two of the horizon, low enough for maximum atmospheric filtering, but still above the horizon providing light. And rain must be present at precisely that moment, with the observer positioned correctly. The window of opportunity is measured in minutes, sometimes only seconds, as the sun touches the horizon and sinks below it. Cultures, throughout history, have attached special significance to red rainbows, often seeing them as omens or blessings of particular power. Some viewed them as especially favorable signs, the warm glow suggesting divine approval. Others saw them as warnings, the blood-red colors suggesting danger or change. The warm glow contrasts sharply with the typical cool tones of a storm, creating a sense of resolution, as though the weather itself is apologizing for its earlier fury with a gift of beauty. In truth, it is simply light behaving according to physical laws, following the same rules it always follows, but the effect is no less moving for being understood. Red rainbows remind us that nature's beauty often depends on timing more than anything else, on being in the right place at the right moment, when multiple conditions align in extraordinary ways that happen rarely but memorably. Polarization creates rainbow-like colors in clouds. Sometimes, even without rain or mist, colors appear in clouds themselves, creating displays that resemble rainbows but form through different physics. These iridescent displays, called cloud iridescence, form when tiny water droplets or ice crystals diffract sunlight, bending it around their edges rather than through their bodies. The result is patches of rainbow-like color, often in beautiful pastel shades of pink, green, blue, and purple, scattered across the cloud's surface in swirling patterns. Unlike rainbows, which form by refraction and reflection inside water droplets, iridescence comes from diffraction and interference, where light waves interact with obstacles near their own size in wavelength. The colors shift and shimmer as the cloud evolves moment by moment, droplets growing or evaporating or moving, creating a living display that changes as you watch. Iridescent clouds are most common in thin clouds near the sun, though looking directly at the sun is dangerous and should never be done without proper protection. Observers often use their hand or a building or a tree to block the sun's direct glare, revealing the colored fringes surrounding it in the nearby clouds. Altocumulus and cirrocumulus clouds, with their small, uniform droplets, are most likely to display iridescence. Lenticular clouds, those lens-shaped clouds that form over mountains, are also famous for iridescent displays. The effect is delicate and easily missed by casual observers, requiring attentive eyes and a willingness to study the sky beyond the obvious features. Once you learn to recognize iridescence and train yourself to look for it, you begin to see it often, perhaps several times a month, a subtle reminder that the atmosphere is always playing with light in ways we usually overlook. Polarized sunglasses can enhance or diminish cloud iridescence dramatically, depending on their orientation. Because the light creating iridescence is partially polarized, rotating your head or your sunglasses by 90 degrees can make the colors intensify dramatically or vanish completely, a simple experiment that reveals the underlying physics at work. This interaction between polarization and color shows that even everyday tools like sunglasses are windows into the behavior of light, giving us new ways to see the world. The colors in clouds may not be rainbows in the strict technical sense, but they share the same fundamental cause: water, in various forms altering the path of sunlight, revealing hidden spectra that exist all around us, but become visible only under specific conditions. Supernumerary rainbows add extra bands of color. Sometimes, if you look carefully at a particularly well-formed rainbow, you might notice something extra and unexpected. Inside the main arc of the rainbow, just below the violet band, additional faint bands of color appear, like ripples on the surface of the primary arc. These are supernumerary rainbows, also called supernumerary arcs or supernumerary bands, and they result from the interference of light waves, a quantum mechanical effect. When light exits a raindrop, different paths taken by light rays overlap in space, and these overlapping waves either reinforce or cancel each other out, depending on their wavelengths and the exact path difference. This interference creates extra bands, usually appearing as pastel shades of pink, green, and violet, stacked just inside the main violet edge of the primary rainbow. They are most visible when raindrops are small and remarkably uniform in size, conditions that allow the interference patterns to remain coherent across many droplets rather than washing out into blur. Supernumerary arcs are delicate and often go unnoticed by casual observers, overshadowed by the brightness and boldness of the main rainbow above them. But once you know to look for them and train your eye to detect these subtle features, they reveal themselves as gentle, repeating patterns of color, like harmonics in a musical note, adding complexity to a fundamental tone. Not every rainbow displays them clearly, and their visibility depends critically on the observer's position and the characteristics of the rain producing the bow. Large, varied droplets of different sizes produce messy interference patterns that blur together into indistinction, while tiny, uniform droplets of similar size create sharp, distinct supernumeraries that can be counted. This makes supernumerary bands more common in drizzle or fine mist than in heavy rain with large drops, and more common early or late in a rain event when drop sizes are more uniform. The discovery of supernumerary arcs in the 19th century helped scientists understand light as a wave rather than just a stream of particles. The interference patterns could only be explained by wave theory, where light waves overlap and interfere like ripples on water, supporting the work of physicists like Thomas Young, who demonstrated light's wave nature. Today, supernumerary rainbows remain a subtle test of atmospheric conditions, a clue to the size and uniformity of raindrops suspended in the air that only careful observers notice. For the casual observer enjoying a rainbow, supernumerary rainbows are simply an extra layer of beauty, a bonus detail in an already stunning display, like finding a hidden treasure within a treasure. Rainbows are circular, not just arcs. From our usual position on the ground, we see rainbows as arcs stretching across the sky. But this is an illusion created by our perspective and the earth beneath our feet. The ground cuts off the lower half of what is actually a full circle of color. If you could view a rainbow from above, perhaps from an aeroplane flying through sunlit skies with rain below you, you would see the complete ring, a perfect circle of color with no beginning and no end. Pilots and passengers occasionally glimpse these circular rainbows, also called glory rings, when they surround the shadow of the aircraft projected onto clouds below. The circle centers on the anti-solar point, the spot in the sky directly opposite the sun from the observer's position, and the aircraft's shadow marks that point precisely, creating a dramatic image of the plane's silhouette surrounded by colored rings. The circular nature of rainbows follows logically from their formation mechanism. Every raindrop, at the correct 42-degree angle from the anti-solar point, contributes to the circle. And since raindrops are scattered throughout the sky in all directions around you, the full 360 degrees can potentially be painted in color if enough drops are present. On the ground, however, we lack the elevated vantage point to see the lower half of the circle. The Earth blocks our view, interrupting the ring and leaving only the upper arc visible above the horizon. This is why rainbows always appear to touch the horizon at both ends, seeming to connect Earth and sky like bridges. In reality, the circle continues below the ground level, invisible but mathematically present, painted on air we cannot see because the Earth is in the way. Circular rainbows can also appear around your own shadow when you stand on a mountain with your back to the sun and mist or clouds below you in the valley. Your shadow falls onto the mist, projected large onto the cloud tops, and the rainbow forms as a glowing halo around your shadow's head, a phenomenon called a Brocken spectre, when combined with magnification effects that make your shadow appear giant. The experience is eerie and beautiful simultaneously, watching your own silhouette surrounded by a ring of color, as though you have become the center of a celestial display or achieved some kind of divine aura. It is a reminder that perspective fundamentally shapes what we see, and that hidden dimensions exist in even the most familiar sights, waiting to be revealed from different viewpoints. The primary rainbow is brightest among the multiple rainbows that can potentially form when conditions are ideal. The primary arc, the first and lowest rainbow in the sky, is always the brightest and most vivid. This is because it involves only one internal reflection inside each raindrop, allowing more light to exit the drop and reach the observer's eyes. Each additional reflection inside the droplet weakens the light significantly, causing it to lose intensity. This is why secondary rainbows are fainter, and higher-order rainbows are barely visible or completely invisible to the naked eye. The primary rainbow displays the full spectrum, with red on top and violet on the bottom, vivid and bold against the sky, immediately commanding attention from anyone who glances in its direction. The brightness of the primary rainbow varies considerably, depending on the intensity of sunlight and the density of raindrops in the air. A bright sun breaking through clouds and heavy rain with large droplets produce the most brilliant rainbows imaginable. Colors so saturated they seem almost unreal or artificially enhanced. Lighter rain or dimmer sun creates paler arcs, still beautiful, but more subdued and delicate. The size of the raindrops also matters significantly. Larger drops, those around a millimeter or more in diameter, produce sharper, more defined rainbows with clear color separation. Smaller drops create softer, more diffuse rainbows, where the colors blend more gradually. This variability means no two rainbows are identical, each a unique combination of light intensity, water density, droplet size, and atmospheric conditions. The primary rainbow's brightness and clarity make it accessible to everyone, not just trained observers or those with perfect conditions. Even in less than ideal conditions, with partial clouds or light rain, it often remains visible, a dependable display when weather and light align. Its constancy across cultures and centuries has made it a universal symbol, recognized by every society that has watched the sky after storms. Whether seen from a mountaintop or a city street, from ancient times or the present day, the primary rainbow is nature's most reliable brushstroke, painting the same curve, the same colors, again and again, with infinite patience and consistency. Ancient cultures wove rainbows into myth long before science explained rainbows through physics and optics. Humans created stories to account for them, weaving them into mythology and religion. In Greek mythology, the rainbow was personified as Iris, a messenger goddess who traveled between the heavens and the earth, her colorful path visible to mortals below as she carried communications between gods and humans. In Norse mythology, the rainbow bridge Bifrost connected Midgard, the world of humans, to Asgard, the realm of the gods high above. Warriors who died bravely in battle were said to cross Bifrost to reach Valhalla, the great hall where heroes feasted. In Chinese legend, the rainbow was sometimes seen as a sky dragon, its arching body linking heaven and earth, or as a crack in the sky being repaired by celestial forces. Many cultures saw rainbows as bridges or pathways, a natural interpretation given their shape and the way they seem to connect distant points on the ground or link earth to sky. Some viewed them as divine promises or favorable omens. In the biblical story of Noah, after the great flood that covered the earth, God placed a rainbow in the sky as a covenant, a pledge never to destroy the world by flood again. This story resonated across generations and cultures, turning rainbows into symbols of hope, renewal, and divine mercy. Other traditions treated rainbows with caution or even fear, seeing them as omens or warnings. Some Aboriginal Australian stories describe rainbow serpents, powerful beings associated with water, creation, and sometimes danger, entities that must be respected and appeased. The diversity of rainbow myths across human cultures reflects their universality. Every culture that experienced rain and sun encountered rainbows, and every culture invented explanations that fit within their existing belief systems and worldviews. These stories often emphasized transformation, connection, or divine communication, themes that resonate even today in modern interpretations. While we now understand the physics of refraction and reflection, the sense of wonder remains fundamentally unchanged. Rainbows still feel like messages from the sky, even if we know the messenger is light rather than gods. And even if we understand the mechanics, the emotional response persists. Rainbows have been studied for thousands of years. Humans have pondered rainbows for as long as they have studied the natural world systematically. Aristotle, the Greek philosopher and polymath, wrote about rainbows in his work Meteorology around 350 BCE, proposing that they were reflections in clouds, images projected onto the sky. He correctly recognized that rainbows always appear opposite the sun in the sky, but he believed they were projections or reflections rather than phenomena involving individual water droplets bending light. His ideas, though incomplete, persisted for centuries, shaping thought in the ancient and medieval worlds and influencing scholars who had access to his writings. It was not until the Islamic Golden Age, from roughly the 8th to the 14th centuries, that scholars like Kamal al-Din al-Farisi and the great scientist Ibn al-Haytham made significant advances in understanding rainbows, using careful experiments with glass spheres filled with water to model raindrops and trace the paths of light rays through them. In the 17th century, René Descartes used mathematics and experimentation to explain how light refracts and reflects inside a raindrop, producing the specific angles necessary for rainbows to form. He calculated the path of light through spherical drops with impressive precision and predicted the 42-degree angle for the primary rainbow and the 51-degree angle for the secondary bow. Isaac Newton later expanded on this work dramatically, demonstrating that white light is composed of a spectrum of colors by passing sunlight through a prism and watching it spread into a rainbow of hues. He then used a second prism to recombine those colors back into white light, proving that the colors were not created by the prism but revealed by it. Together, Descartes' and Newton's efforts laid the foundation for modern optics and our understanding of light. Today, rainbows are not mysterious or supernatural, but they remain subjects of ongoing study. Atmospheric scientists examine them to understand precipitation patterns, cloud formations, and droplet-size distributions. Photographers chase them as artistic subjects, traveling to remote locations and timing their visits to maximize their chances. Educators use them to teach physics, optics, and the nature of light and color. The progression from myth to science has not diminished their appeal or wonder. If anything, understanding how rainbows form deepens appreciation for their beauty. They are no longer omens from capricious gods or magical bridges to other realms, but expressions of natural law, predictable and repeatable through physics, yet no less wondrous for being understood. Rainbows and water droplet size. The size of water droplets suspended in the air profoundly affects the appearance of rainbows in multiple ways. Large raindrops, those bigger than a millimeter in diameter, create the brightest and most vivid rainbows, with clearly defined color bands that transition sharply from one hue to the next. The colors appear saturated and pure, creating the classic rainbow appearance we picture in our minds. As droplets shrink in size, rainbows become paler and wider, their colors washing together more gradually. The boundaries between red and orange, between blue and violet, become less distinct. When droplets are very small, less than 1/10 of a millimeter in diameter, the rainbow may fade almost entirely or transform into a fog bow, appearing white and ghostly rather than colorful. This relationship between droplet size and rainbow appearance reveals information about the rain itself, allowing meteorologists to infer characteristics of the precipitation. They can estimate whether rain is heavy or light, whether drops are fresh and large, or evaporating and shrinking, simply by observing the sharpness and saturation of a rainbow's colors. Uniform droplet size enhances supernumerary arcs, those faint extra bands of color that sometimes appear inside the main rainbow. When drops vary widely in size within the same rain shaft, interference patterns blur and cancel each other out, and supernumeraries disappear into the background. This makes supernumerary rainbows a sign of uniform conditions, often associated with steady, gentle rain, rather than chaotic downpours with drops of many sizes. The precision required for these subtle details shows how sensitive rainbows are to their environment. A slight change in rain intensity, a shift in wind carrying drops of different sizes from different parts of the cloud, and the rainbow's character changes noticeably with it. Water droplets are not perfect spheres when they are large enough to be affected by aerodynamics. As they fall through air resistance flattens them slightly into oblate shapes, wider than they are tall, like hamburger buns rather than balls. This distortion slightly alters the angles of light refraction, subtly affecting the rainbow's appearance in ways that are mostly imperceptible to casual observers, but measurable with instruments. For most observers and most purposes, the assumption of spherical drops is accurate enough, but the flattening demonstrates the complexity hidden within a seemingly simple phenomenon. Every rainbow is shaped by countless variables: droplet size, shape, distribution through space, uniformity, sunlight intensity, atmospheric clarity, and observer position. That any two rainbows manage to look similar is actually a testament to the consistency and reliability of physical laws operating across all these variables. Rainbows and the horizon. The lower the sun sits in the sky, the higher the rainbow arches above the horizon. This relationship is geometric, mathematical, and absolutely fixed by the laws of optics. When the sun is exactly at the horizon, at sunrise or sunset, the antisolar point is also at the horizon on the opposite side of the sky, and the rainbow can arch as high as 42 degrees above that opposite horizon, creating a towering semicircle spanning much of the visible sky. As the sun climbs higher throughout the morning, the antisolar point drops lower, and the rainbow sinks with it, becoming smaller and lower in the sky. By the time the sun reaches an altitude of 42 degrees above the horizon, the rainbow's top barely touches the horizon at the anti-solar point, and the arc becomes impossible to see. Beyond this critical angle, rainbows cannot form in rain because the entire 42-degree cone would be below ground level. This means rainbows are physically impossible when the sun is high in the sky, a fact that limits their appearance to mornings and late afternoons in temperate latitudes during most of the year. Near the equator, where the sun climbs nearly straight overhead every day, midday rainbows are rare or impossible for much of the year. Possible only during the periods around the equinoxes, when the sun's path is lower. Near the poles, where the sun skims the horizon for much of the year during summer months, rainbows can appear at any time of day as long as both sun and rain are present. Geography and season thus dictate not just whether rainbows appear, but when they appear, and how high they rise above the landscape. This variability adds to their specialness and rarity in certain locations. In some places and times, rainbows are relatively abundant, appearing several times per week during rainy seasons. In others, they are rare treasures, appearing only a few times per year, making each sighting more precious and memorable. The relationship between sun position and rainbow geometry also means that rainbows orient themselves relative to the individual viewer's perspective. Turn your head, and the rainbow moves correspondingly with your perspective, maintaining its position relative to the anti-solar point. Walk toward where the rainbow appears to touch the ground, and it recedes at exactly the same pace you advance, always staying at that 42-degree angle. Run away from it, and it follows you, maintaining its angular distance. This impossibility of approach frustrated treasure hunters in folklore who believed gold or other treasures lay at the rainbow's end, a myth we will explore shortly. In truth, the rainbow has no end, no fixed location in physical space. It is an angle, a direction, a geometric relationship, a marriage of sunlight and water, and vision that exists only in the seeing, requiring all three elements to manifest. The rainbow's end and the myth of gold. The legend of a pot of gold hidden at the rainbow's end is ancient and widespread, appearing in Irish folklore, European fairy tales, and stories from cultures around the world. The myth likely arose from the rainbow's tendency to appear to touch the ground at its two ends, where the arc meets the horizon, creating the illusion of specific locations that could potentially be reached. Early peoples, noticing this apparent contact with the earth, might have imagined that something must be there at those spots, some treasure or significance marking the locations where heaven touches earth. The fact that rainbows move as you move, making the end perpetually out of reach no matter how fast you run or how far you travel, only added to the mystery and the allure, suggesting that the treasure was protected by magic or divine will. In reality, rainbows have no ends in the sense of specific locations you could reach. They are circles when viewed from the right perspective, and what appears to be the end is simply where the arc intersects our line of sight to the horizon, where our vision projects the 42-degree angle onto the ground. If you could travel to that spot, running or driving to where the rainbow seems to touch down, the rainbow would move ahead of you, maintaining its angular distance as you approach. The 42-degree angle from your eye to the anti-solar point is fixed by physics, so the rainbow maintains that relationship no matter where you stand. No amount of walking or running will bring you any closer to it. This unreachability may have actually contributed to the myth of treasure rather than dispelling it. Something so beautiful, yet so unattainable, must surely guard something valuable, a reward for those clever or persistent or blessed enough to reach it. The myth endures in modern culture because it captures something emotionally true about rainbows, even if it is physically false. They represent hope and promise, things worth pursuing, even if they remain just beyond reach. The journey toward a rainbow, even knowing intellectually that it is futile, becomes a metaphor for chasing dreams or seeking beauty for its own sake rather than for possession. That we can never touch a rainbow or reach its end does not diminish its worth or our desire to try. If anything, its intangibility makes it more precious, a gift meant to be admired and appreciated from afar, rather than possessed or controlled. The rainbow teaches us that some things have value precisely because they cannot be grasped, and that beauty exists independent of ownership. Reflected rainbows can appear in water. When a rainbow appears over a body of water, such as a lake or ocean or large river, sometimes a second arc appears below it, seemingly mirrored on the water's surface. This is a reflection rainbow, distinct from a secondary rainbow, and it forms when the primary rainbow's light reflects off the water's surface before reaching the observer's eyes. Reflection rainbows follow the same optical rules as their standard counterparts, but appear lower in the sky and slightly offset in position, creating a doubling effect that can be stunning. The water must be calm enough and large enough to act as an effective mirror, reflecting light efficiently. Rippled or rough surfaces scatter the light in many directions and blur the reflection into indistinction, so reflection rainbows require still conditions. Reflection rainbows are considerably rarer than standard rainbows because they require multiple conditions to align perfectly simultaneously. A rainbow must be present. A body of water must be in the right location relative to the rainbow and observer. The water must be calm, and the observer must be positioned so that the reflected light reaches their eyes at the proper angle. When all these factors coincide, the effect is stunning and photogenic. Two arcs stacked vertically in the scene, the lower one inverted like a mirror image, as though the sky and water are conversing in color. Photographers prize these shots highly, the symmetry and doubling adding layers of beauty to an already beautiful scene, creating compositions that feel almost too perfect to be natural. Occasionally, under absolutely perfect conditions that align like cosmic tumblers in a lock, a reflected rainbow can appear alongside a standard double rainbow, creating 4 arcs in total, 2 in the sky, 1 primary and 1 secondary, and 2 reflected in the water below, mirroring the 2 above. Such displays are exceedingly rare, requiring not just calm water and bright sun, but also the precise angles and light intensity needed for both secondary and reflected bows to form simultaneously. Witnessing one of these quadruple displays feels like winning a natural lottery, a convergence of circumstances so unlikely it seems, orchestrated by some benevolent force, a gift from the universe to those present at exactly the right place and time. Rainbows and polarization. The light in a rainbow is partially polarized, meaning the light waves vibrate, predominantly in one direction, rather than vibrating randomly in all directions equally. This polarization occurs during the internal reflection inside the raindrop. When light bounces off the back surface of the drop, some orientations of light wave vibration reflect more efficiently than others do, creating a preference for certain vibration directions in the exiting light. Polarized sunglasses can detect this property, often making rainbows appear brighter or dimmer depending on how the glasses are oriented relative to the rainbow. Rotate your head while wearing polarized lenses and watching a rainbow, and you may see the rainbow intensify dramatically or fade significantly, revealing the hidden organization of its light that our eyes cannot normally detect. Birds and many insects can detect polarization naturally without any aids, using it for navigation and orientation as they fly. To them, A rainbow may appear very different than it does to human eyes, perhaps containing patterns or information we cannot perceive at all with our biological equipment. Some scientists speculate that polarization sensitivity could reveal details about raindrops' shape and orientation in space, information encoded in the light but invisible to human perception. This hidden dimension reminds us that our senses show us only part of physical reality, one version tailored to human neurobiology. Other creatures experience the same rainbow through different filters, seeing aspects we can only measure with instruments, living in a sensory world that overlaps ours but is not identical. Polarization also affects how rainbows interact with reflections and multiple scattering in complex atmospheric conditions. In situations where light bounces between multiple layers of rain or mist or cloud, polarization can enhance or diminish different parts of the display in ways that are difficult to predict without detailed modeling. Understanding these effects helps scientists model atmospheric optics more accurately and predict when rainbows will be most visible and vivid. For the casual observer simply enjoying a rainbow, polarization is simply another layer of physics woven into the rainbow's beauty, mostly invisible but always present, shaping what we see in subtle ways we don't consciously notice, but that affect the overall impression nonetheless. Rainbows can appear in the spray of whales. When whales surface and exhale through their blowholes, they send dramatic plumes of water vapor and mist into the air above the ocean's surface. On sunny days, these plumes catch the light and create tiny rainbows, small arcs that last only seconds before the spray disperses and falls back to the water. Whale watchers on boats treasure these moments, when the majesty of a breaching whale or surfacing pod combines with the delicate beauty of a rainbow born from the whale's breath itself. The physics is identical to any rainbow, sunlight refracting through water droplets, suspended in air, but the source makes it feel special and magical, a collaboration between ocean and atmosphere, animal and light, mammal and physics. Ship spray can create similar rainbows wherever boats cut through waves. The bow wave, where water breaks against the hull as the vessel moves forward, throws mist constantly into the air, and on sunny voyages, these tiny rainbows accompany the vessel, dancing at the edge of vision for as long as the ship maintains speed. Sailors have seen them for centuries during their voyages, colorful companions on long journeys across empty oceans. They serve no practical purpose except beauty, ephemeral decorations provided by physics and motion meeting sunlight at the right angle. Any spray, from any source whatsoever, can birth a rainbow given the right angle of sun and observer and sufficient droplet density. Garden sprinklers, breaking surf, mist from a sneeze in bright light, even spray from a pressure washer, all follow the same rules of refraction without exception. This universality is part of the rainbow's charm and democratic nature. It does not discriminate by scale or source or worthiness. A whale's breath and a child's garden hose are equally capable of bending light into color. The phenomenon plays out endlessly, in contexts grand and mundane, always faithful to the geometry that governs it, indifferent to the source of the water or the reason for its presence in air. Rainbows have inspired art for centuries. Artists have tried to capture rainbows on canvas, in sculpture, in poetry and music, for as long as humans have created art. The challenge is considerable, and perhaps ultimately insurmountable. Rainbows are luminous, glowing with light that paint or pigment cannot easily replicate, since paint absorbs rather than emits light. Their colors are pure and saturated, difficult to match with pigments that are inherently duller than pure spectral colors. Yet artists persist, drawn to the rainbow's symbolism and beauty despite the technical challenges. From medieval illuminated manuscripts to contemporary light installations, rainbows appear as motifs representing hope, diversity, transition, transcendence, promise, and countless other symbolic meanings. The Romantic painters of the 19th century often included rainbows in their landscapes, using them to convey mood, emotion, and meaning beyond mere depiction. John Constable's famous painting, Salisbury Cathedral from the Meadows, features a dramatic rainbow arching over the cathedral, suggesting divine presence, promise, or blessing. The Hudson River School artists in America painted rainbows over pristine wilderness, linking natural beauty with spiritual significance and divine creation. These works captured not just the physical appearance of rainbows as accurately as possible, but their emotional resonance, the way they transform scenes and stir feelings in those who witness them. Modern and contemporary artists have explored rainbows in abstract and conceptual ways beyond realistic depiction. Light installations use prisms and water to generate real rainbows in galleries and museums, turning the phenomenon itself into sculpture and making the process visible to viewers. Others use rainbow colors symbolically, as in the rainbow flag representing LGBTQ+ pride, adopted in 1978 by Gilbert Baker, and now recognized worldwide as a symbol of diversity and inclusion. In this context, the rainbow's spectrum of colors represents diversity and unity, a visual metaphor for many differences coexisting harmoniously. The rainbow's journey from purely natural phenomenon to cultural symbol shows its power to mean many things, adapting to human needs and imagination while retaining its visual identity. Superstitions and beliefs surround rainbows. Different cultures throughout history have held varied beliefs about rainbows, some positive and welcoming, others cautionary or fearful. In parts of West Africa, rainbows were considered potentially dangerous, associated with snakes or spirits that could harm those who looked directly at them or pointed at them. Children were warned not to point at rainbows with their fingers, lest misfortune follow in the form of warts, crooked fingers, or bad luck. In contrast, many European traditions saw rainbows as good omens without qualification, signs of fair weather to come after storms or blessings from above. Sailors particularly welcomed rainbows as indicators that storms were passing and calmer seas lay ahead, making them symbols of safety and hope. Some Native American traditions viewed rainbows as pathways for spirits or bridges to other realms beyond the physical world, places where the living could not safely go. In Hawaiian belief, rainbows are strongly associated with royalty and considered manifestations of divine presence, particularly of gods and high chiefs. Seeing a rainbow in Hawaii is still widely regarded as auspicious, a sign of favor or blessing, particularly if it appears during significant events. In Japan, rainbows occasionally appear in folklore as bridges used by deities or as symbols of renewal and hope after hardship. The variety of beliefs reflects the rainbow's profound impact on human consciousness across widely separated cultures. Its ability to provoke awe and demand interpretation regardless of geographical or cultural context. Even in the modern era, with scientific understanding widespread, rainbows retain symbolic weight in popular culture and personal experience. They appear on greeting cards as symbols of hope sent to those experiencing hardship, on motivational posters as reminders that storms pass and beauty returns. The phrase "chasing rainbows" means pursuing impossible dreams or unlikely goals, yet it is not entirely dismissive or negative. It acknowledges the human tendency to seek beauty and meaning, even in things we cannot possess or achieve. Rainbows occupy a unique space in our collective imagination, bridging the gap between scientific understanding and emotional resonance. simultaneously explained and mysterious, understood and wondrous. The speed of light governs rainbows. Rainbows exist fundamentally because light has a finite speed, and that speed changes depending on the medium through which light travels. In vacuum, the ultimate empty space, light moves at approximately 299,792 kilometers per second, the cosmic speed limit that nothing can exceed. In air at sea level, it slows just slightly, imperceptibly to human perception, but measurably with instruments. In water, it slows significantly, to about 3/4 of its vacuum speed, around 225,000 kilometers per second. This change in speed causes refraction, the bending of light at the boundary between air and water. Without this speed difference between the two media, light would pass straight through raindrops without bending or separating, and rainbows would not exist at all. The entire phenomenon depends on this simple fact: light slows down in water. The relationship between speed and refraction angle is expressed mathematically in Snell's law, a formula discovered independently by multiple scientists over centuries as they studied optics. It calculates exactly how much light will bend based on the angle at which it strikes the boundary and the refractive indices of the two materials, which are related to light's speed in those materials. For water and air, the refractive index ratio means that light entering a raindrop at a glancing angle will bend significantly inward, while light entering nearly straight on will barely bend at all. This variation in bending depending on entry angle creates the range of angles that ultimately form the rainbow's arc shape. Understanding the speed of light and measuring it accurately was crucial to understanding rainbows fully. Early optical theories sometimes proposed that light traveled instantaneously from source to eye, which could not adequately explain refraction or other optical phenomena. Once scientists measured light speed, first roughly by Römer in 1676, by observing Jupiter's moons, and later with increasing precision, and recognized its finite nature, the behavior of light in different materials made complete sense. Rainbows became proof of light's wave nature and its interaction with matter governed by speed changes. They are, in essence, visible evidence of fundamental physics, beauty emerging naturally from the laws that govern reality at its deepest level. Rainbows and human emotion. Rainbows evoke strong emotional responses in people across cultures and ages. Psychological studies show that seeing a rainbow can measurably improve mood, reduce stress levels, and inspire feelings of hope and wonder in both children and adults. This response is likely partly cultural and learned through stories and associations, but it is also deeply rooted in practical experience. Rainbows appear after storms, marking the return of clear skies and sunlight after danger and darkness. They signal that danger has passed, that the world is returning to balance, that the threatening weather is moving away. For our ancestors living more directly exposed to weather, this association with safety and renewal would have been practically meaningful and emotionally significant. Today, even though we understand rainbows scientifically and live mostly sheltered from weather, that emotional connection persists across generations. The colors themselves may contribute significantly to the emotional response. Bright, saturated colors stimulate the visual system and can affect mood and arousal levels. The full spectrum displayed in a rainbow includes warm colors like red and orange, which are energizing and exciting, and cool colors like blue and violet, which are calming and soothing. Seeing all of them together in sequence creates a balanced, harmonious experience that satisfies our aesthetic sense. Some color theorists and psychologists suggest that rainbows appeal to us because they present the full range of visible light in its natural order. a completeness and wholeness that feels intrinsically right or pleasing to our perception systems. Rainbows also inspire a sense of connection and shared experience. When one appears, people often call out to others, pointing and sharing the moment with whoever is nearby. Strangers smile at each other, united temporarily by the shared experience of witnessing beauty. In this way, rainbows act as social catalysts, brief events that bring people together across normal social boundaries. This communal aspect may enhance their emotional impact beyond what the visual experience alone would create. Seeing a rainbow alone is wonderful and moving. Seeing it with others amplifies the joy through shared appreciation and mutual acknowledgement of beauty. Rainbows and wavelengths of light. Each color in a rainbow corresponds to a specific wavelength of electromagnetic radiation in the visible spectrum. Red light has the longest wavelength visible to human eyes, measuring approximately 700 nanometers from peak to peak. Violet has the shortest wavelength we can perceive, around 380 to 400 nanometers. Between them lie all the other colors we can see, each defined precisely by its wavelength. This spectrum is continuous rather than discrete, meaning there are infinite gradations of color between red and violet, an uncountable infinity of subtle shades. We perceive only a selection from this continuum, grouped into color categories by our brains and influenced by our culture. Some languages have more words for distinct colors than others, dividing the spectrum differently. Yet the physical rainbow remains the same, regardless of how we name its parts. Wavelength determines not just the color we perceive, but how light interacts with matter at a fundamental level. Shorter wavelengths like violet carry more energy and bend more sharply when entering water, which is why violet appears on the inside of a rainbow at the smaller angle. Longer wavelengths like red carry less energy and bend less dramatically, positioning them on the outside of the arc at the larger angle. This precise relationship between wavelength and refraction angle is mathematical, predictable, and invariant, allowing scientists to calculate exactly where each color will appear in a rainbow based solely on the wavelength and the refractive properties of water. The elegance of this relationship, where something as abstract as wavelength translates directly into the concrete beauty of color arranged in space, is part of what makes rainbows so fascinating to study scientifically. Beyond visible light, wavelengths extend into regions we cannot see with our eyes alone. Ultraviolet light has wavelengths shorter than violet, extending down to about 10 nanometers before transitioning into X-rays. Infrared has wavelengths longer than red, extending upward through heat radiation. Some animals can detect ultraviolet light, including certain birds, insects like bees, and some reptiles. To them, rainbows may contain an extra band of color beyond violet that humans cannot perceive, an eighth color invisible to our biology. Similarly, infrared wavelengths exist beyond red, detectable only with instruments like thermal cameras. The rainbow we see is bounded and limited by our human biology, a selection from a broader electromagnetic spectrum that exists whether we perceive it or not, reminding us that reality extends beyond our senses. The science of raindrop shape and its effects. Raindrops are not teardrop-shaped, despite how they are commonly drawn in cartoons and illustrations. Small raindrops, those smaller than about a millimeter in diameter, are nearly perfect spheres, held together by surface tension into the most compact shape possible. As drops grow larger through coalescence or continued condensation, air resistance during their fall through the atmosphere begins to deform them. The bottom flattens due to air pressure, while the top remains rounded, creating a shape more like a hamburger bun than a sphere or teardrop. Rounded on top, and flat or even slightly indented below. Very large drops, those approaching 5 millimeters in diameter, become unstable under these forces and break apart into smaller droplets, which is why raindrops in natural rain never exceed this size significantly. This progression of shapes affects how light refracts through them, though for most rainbow calculations, the assumption of spherical drops is accurate enough to produce correct predictions. The spherical shape of small and medium raindrops is crucial to rainbow formation and explains why rainbows are so common and consistent. A sphere refracts light symmetrically in all directions, creating consistent angles that produce the clear, circular arc we recognize. If raindrops were irregularly shaped with random forms, light would scatter in chaotic, unpredictable directions, and rainbows would be blurry or non-existent, replaced by diffuse glows without clear structure. Nature's tendency towards spherical droplets through the action of surface tension is precisely what makes rainbows possible. The physical properties of water, its surface tension, density, and interaction with air conspire naturally to create the conditions necessary for this optical phenomenon without any design or intention. Scientists have studied raindrop shapes extensively using high-speed photography, wind tunnels, and computer models to understand precisely how they behave as they fall. This research has applications far beyond explaining rainbows, informing weather prediction, radar technology, climate modeling, and understanding of precipitation processes. But it also deepens appreciation for rainbows themselves when you understand the physics at this level. Knowing that each droplet is a tiny lens, shaped by forces invisible to the eye, perfectly formed by natural processes, refracting light according to precise laws of physics, adds layers of wonder to the simple act of seeing an arc of color in the sky after rain. Rainbows in waterfalls are nearly permanent. Unlike rainbows born from passing showers that last only minutes, those that form in the constant mist of waterfalls are nearly permanent features. As long as the sun shines and water falls, the rainbow remains visible, though it may shift position gradually as the sun moves across the sky throughout the day. Waterfalls like those in Yosemite National Park, in Iceland, or at Victoria Falls on the Zambezi River are famous for their reliable rainbows, drawing visitors from around the world who know they can witness these displays almost on demand if they arrive during daylight hours. The predictability does not diminish their beauty in the slightest. If anything, it enhances it, offering a dependable source of wonder in an otherwise unpredictable world, where so much is uncertain. Morning and late afternoon are typically the best times for waterfall rainbows, when the sun is low enough to illuminate the mist at favorable angles matching the 42-degree requirement. Midday rainbows are possible if the waterfall is oriented correctly relative to the sun's overhead position, but the low angle requirement generally limits prime viewing to certain hours unless the waterfall faces in a particularly favorable direction. During these optimal windows, the rainbows can be extraordinarily vivid and saturated, the constant supply of fresh mist ensuring optimal conditions continuously. The roar of falling water, the cool spray on your skin, the negative ions in the air, and the brilliant colors overhead combine into an immersive, multi-sensory experience that engages more than just vision. Waterfall rainbows also offer opportunities to see phenomena rarely visible in rain-born rainbows, such as supernumerary arcs, fogbows near the waterfall, base where mist is finest, and reflected rainbows in pools below. The consistency of droplet size and density creates ideal conditions for these subtle effects to manifest clearly. For photographers and scientists, waterfalls serve as natural laboratories, places where rainbows can be studied and documented with patience and precision. returning day after day to the same location to observe variations. For casual visitors, they offer nearly guaranteed beauty, a reliable encounter with one of nature's most beloved phenomena. Rainbows and lightning, a rare combination. Though uncommon, it is entirely possible to see a rainbow and lightning simultaneously in the same sky. This requires very specific conditions. A storm must be actively leaving an area, allowing sunlight to break through the trailing edge, while rain still falls. And lightning must continue to flash within the departing storm clouds. The juxtaposition is dramatic and somewhat surreal, the gentle curved colors of the rainbow contrasting sharply with the violent, jagged energy of lightning bolts. Photographs capturing both phenomena together are highly prized by weather photographers and storm chasers, symbolizing the duality of nature, its simultaneous capacity for both beauty and power, gentleness and violence, existing in the same moment. The occurrence of rainbows and lightning together speaks to the transitional and dynamic nature of weather systems. Storms are not static entities, but constantly evolving systems, and the moments when they break apart or move through an area create complex and layered atmospheric conditions. Sunlight may penetrate gaps in the clouds, while the storm's core remains active, still producing lightning from the electrical charges built up within. In these liminal moments of transition, the sky becomes a theatrical stage where multiple phenomena share space simultaneously. The rainbow represents order and light emerging from chaos, while the lightning embodies the storm's lingering energy and power, both coexisting briefly. Witnessing this rare combination is deeply memorable, the kind of moment people describe to friends and family for years afterward. It reminds us that nature is not monolithic or simple, but layered and complex, capable of simultaneous expressions that seem contradictory but are simply different aspects of the same atmospheric processes. The same sky that threatens with electrical discharge also offers the promise and beauty of a rainbow, both emerging from the interaction of water and light and energy. This duality mirrors human experience in many ways, where difficult moments often contain seeds of beauty, and transitions hold both danger and hope simultaneously within them. Alexander's band between double rainbows. When a double rainbow appears with both primary and secondary arcs visible, the region of sky between the two arcs looks noticeably darker than the sky above the secondary rainbow or below the primary rainbow. This dark band is called Alexander's band or Alexander's dark band, named after Alexander of Aphrodisias, who first carefully described this phenomenon nearly 2,000 years ago in ancient Greece. The darkness is not actually an absence of light entering that region, but a relative dimming caused by the precise geometry of rainbow formation. Light that would normally scatter into this region is instead preferentially directed into the angles occupied by the primary and secondary rainbows themselves, leaving the band between them comparatively starved of scattered light and therefore appearing darker. The boundaries of Alexander's band are surprisingly sharp when viewing a well-defined double rainbow, making the transition from bright sky to dark band quite noticeable to careful observers. This sharp contrast enhances the visibility of both rainbows dramatically, framing them against a darker background that makes their colors stand out more vividly. Observers often notice the dark band before they even notice the secondary rainbow itself, the darkening drawing the eye upward to where the fainter secondary arc resides. The effect is subtle but striking once you know to look for it, a reminder that rainbows shape not just where light goes, but also where it does not go, creating patterns of light and shadow across the sky. Understanding Alexander's band required significant advances in optical theory beyond basic refraction. Early explanations were speculative, and often incorrect. But Descartes and later scientists used increasingly sophisticated mathematics to show exactly why the band forms and to predict its precise position and width. The angles at which light exits from raindrops cluster around the primary rainbow angle at 42 degrees and the secondary rainbow angle at 51 degrees, leaving the region between them receiving less scattered light than regions outside this range. This precision, where mathematics and geometry predict visible features in the sky, demonstrates the power of scientific inquiry and mathematical modeling to explain and predict beauty in nature. Rainbows and the curve of the horizon. The curvature of a rainbow arc matches the curve of Earth's horizon in a visually pleasing way, though the two curves are not directly causally related. Rainbows are arcs because of the geometry of light refraction at a constant angle, not because they follow Earth's surface. Yet when a rainbow appears to touch the horizon at its two ends, its curve aligns visually with the curve of the world beneath it, creating a sense of harmony and natural fit. From high altitudes, where both Earth's curvature and potentially the rainbow's full circular nature are visible, this alignment becomes even more apparent and beautiful. Two curves nested together, one made of rock and water, the other of pure light and suspended moisture. The horizon acts as a natural boundary and frame for rainbows, cutting them off at ground level and defining their visible extent. On the ocean, or vast flat plains, where the horizon is distant and unobstructed by terrain, rainbows can stretch incredibly wide, their apparent ends far apart, spanning enormous angles of sky. In mountainous regions, where terrain breaks the horizon into irregular, jagged lines at various distances, rainbows may appear fragmented, with sections visible in valleys, while others hide behind peaks or ridgelines. The landscape shapes the rainbow's frame, determining how much of the theoretical circular arc we can actually see from our position. This interaction between rainbow and horizon reminds us that what we see depends critically on where we stand and what surrounds us. The same rainbow looks different from different locations, its shape and visible extent altered by perspective and geography and local terrain. Beauty is not just inherent in the object being observed, but emerges from the relationship between object, observer, and environment, all three contributing to the experience. Rainbows teach this lesson gently and repeatedly, showing us that wonder emerges from the meeting and interaction of many factors, all necessary, all contributing their part to the whole. Rainbows can appear in fire, smoke, and spray. When wildfires burn and firefighting helicopters or planes drop water to combat them, rainbows sometimes appear in the spray, arcing through the smoke-filled air. The water droplets catch sunlight, even amidst the smoke and chaos of the fire, creating arcs of color against the dark backdrop of fire and ash and smoke. These rainbows are incongruous and almost jarring, beautiful moments within destruction, stark reminders that physics operates without regard to context or appropriateness. The light refracts through water, according to the same unchanging laws, whether the water falls from peaceful rain clouds or from the buckets and tanks of firefighting aircraft over burning forests. Smoke itself can significantly affect the appearance of rainbows when present in quantity, scattering light through tiny particles and altering the balance of colors. Fine smoke particulates in the air preferentially scatter shorter wavelengths, which can shift the spectrum and make rainbows appear redder or dimmer than they would in clear air, similar to how sunsets appear red. The combination of smoke and water mist creates complex atmospheric conditions where multiple types of scattering and refraction occur simultaneously, interfering with each other. Despite these distortions and complications, rainbows persist, their fundamental geometry strong enough to withstand significant interference and still produce recognizable arcs that we identify immediately. The presence of rainbows in such difficult circumstances carries symbolic weight for many observers. In the midst of disaster and destruction, a reminder of beauty and natural order appears, suggesting resilience and hope despite hardship. This symbolism is not inherent to the rainbow itself, which forms without intention or meaning or awareness, but humans naturally assign it anyway. We are meaning-making creatures who seek patterns and significance, especially in difficult moments. And a rainbow appearing amidst fire provides a narrative of survival and hope, a sign that not everything is lost, that beauty persists even in darkness. The rainbow's role in navigation. Before modern instruments like compasses and GPS, travelers sometimes used rainbows as indicators of weather patterns and relative direction. A rainbow always appears opposite the sun, so seeing one tells you where the sun is located even if clouds obscure it from direct view. In the morning, a rainbow in the west indicates with certainty that the sun is rising in the east behind you. In the evening, a rainbow in the east means the sun is setting in the west behind you. This simple and reliable relationship provided directional information to those attuned to nature's signs and willing to read them carefully. Rainbows also signal that rain is ending or moving away from your location, useful information for anyone caught outdoors without shelter. The appearance of a rainbow strongly suggests that the storm has passed your position or is currently passing, and clearer weather is approaching from the direction of the sun. For sailors on the ocean, a rainbow astern, behind the ship, meant the weather system they had just sailed through was improving, conditions becoming more favorable. A rainbow ahead of the ship suggested rain and potential storms in their path, warning them of conditions to come. These observations were practical rather than mystical, based on understanding atmospheric patterns, wind directions, and light behavior. While navigation by rainbow is unnecessary today, with modern technology providing precise positioning and weather information, the principle remains completely valid. Rainbows still provide accurate information about sun, position, and weather movement direction to anyone who notices and interprets them correctly. The skill lies in paying attention, in reading the sky's signals, rather than relying solely on electronic devices. This connection to the natural world, using observation and inference derived from understanding basic principles, is something many people find deeply satisfying, a way of engaging with the environment that technology has largely replaced, but not entirely erased or made irrelevant. Rainbows in literature and song, writers and poets have invoked rainbows for centuries as symbols and metaphors in their works. William Wordsworth's poem, My Heart Leaps Up, celebrates the joy of seeing a rainbow, linking it to childlike wonder and continuity across a lifetime from childhood to old age. The Rainbow Connection, from the Muppet movie, asks what lies beyond the rainbow, using it as a metaphor for dreams, hopes, and possibilities that may or may not exist. The rainbow appears in fairy tales, spiritual texts, popular songs, and literary fiction, almost always carrying connotations of hope, transition, promise, beauty, or otherworldly connection. The universality of rainbow imagery across cultures and languages speaks to its deep emotional resonance with human experience. Regardless of language, culture, or historical period, the rainbow's appearance and ephemeral nature make it a natural symbol for things that are beautiful but fleeting, present but ungraspable, real but intangible. Writers use it to evoke specific feelings, knowing readers will bring their own associations and experiences to the image. The rainbow becomes a shared reference point, a piece of nature that virtually everyone has seen at some point, and that therefore can represent communal experiences of wonder, hope, or longing that transcend individual circumstances. In some narratives, rainbows represent barriers or thresholds, boundaries between the mundane world and the magical or spiritual realms. Characters who cross a rainbow or reach its end often enter enchanted realms or experience profound transformations in these stories. This trope draws on ancient myths of rainbow bridges, but persists in modern fantasy literature and film, showing that rainbows continue to capture our imagination as portals or bridges between worlds. Even when we know scientifically they are phenomena of light and water rather than actual pathways, the persistence of this imagery shows how deeply rainbows are embedded in human storytelling and myth-making. The shortest and longest rainbows. The duration of any rainbow depends entirely on how long sunlight and rain coexist in the correct geometric configuration. Some rainbows last only seconds, flashing into existence as a brief sunbreak coincides with passing rain, then vanishing instantly as clouds close or rain ends. A gap in clouds allows a single beam of sunlight through for just a moment, creating a brief arc before being cut off again. Others linger for 30 minutes or more, especially when slow-moving weather systems maintain steady rain while the sun shines continuously from a clearing sky. The longest-lasting rainbows occur during prolonged transitions between weather fronts, where conditions hover in unstable balance for extended periods. The record for the longest-lasting rainbow is difficult to verify definitively due to the challenges of continuous observation, but reports exist of rainbows visible for several hours under exceptional circumstances. In 1994, residents of Wetherby, England, observed a rainbow that reportedly persisted for over 3 hours, maintained by a slow-moving weather system that kept rain and sun in the correct alignment throughout the afternoon and early evening. Such events are extremely rare, requiring unusual atmospheric stability and very specific wind and pressure patterns. Most rainbows are fleeting by comparison, measured in minutes rather than hours, which is fundamentally part of their charm and appeal. They come and go quickly, gifts of perfect timing that must be appreciated immediately or missed entirely. Short-lived rainbows lasting only seconds can be intensely beautiful, precisely because of their extreme brevity. A rainbow that lasts only 5 seconds feels like a secret shared with very few, a glimpse of something rare that only those looking at exactly the right moment will see. Those who happen to be watching at that instant see it. Everyone else misses it entirely, perhaps never knowing it existed. This element of chance and randomness adds to the sense that rainbows are special occurrences, that witnessing one involves an element of luck or being in the right place at the right time. Whether lasting seconds or hours, each rainbow is ultimately temporary, a reminder that beauty need not endure forever to be meaningful or profound. Rainbows across the solar system. Rainbows as we know them require liquid water droplets and sunlight, conditions that are, unfortunately, rare beyond Earth in our solar system. However, other planets and moons with atmospheres and liquids might theoretically host rainbow-like phenomena under certain conditions. Titan, Saturn's largest moon, has lakes and rain made of liquid methane and ethane rather than water. If sunlight manages to penetrate Titan's thick, hazy atmosphere sufficiently, it might refract through methane droplets, creating something analogous to a rainbow, though the colors and angles would differ from Earth rainbows due to methane's different refractive index compared to water. Such a rainbow would be alien and strange, governed by the same underlying physics but expressed in unfamiliar ways we can only imagine. Venus has dense clouds composed of sulfuric acid droplets rather than water. and in principle, these could refract sunlight into spectra. However, Venus's extraordinarily thick cloud layer blocks most direct sunlight from reaching the lower atmosphere, where droplets are dense enough, making rainbows unlikely or impossible under normal conditions. Mars has occasional water-ice clouds and possibly brief liquid water under certain localized conditions, but its thin atmosphere and generally cold temperatures make rainbows exceedingly rare or perhaps impossible. If Martian rainbows occur at all, they would be faint and brief, visible only under extraordinary and fleeting circumstances that align rarely. The possibility of rainbows on other worlds reminds us that beauty and optical phenomena are not unique to Earth, but our planet's specific conditions make it a particularly vibrant and favorable place for such phenomena. Liquid water in abundance, relatively clear atmosphere, and plentiful sunlight create an ideal environment for rainbows to form frequently. As we explore the solar system and eventually beyond, we may discover other forms of optical beauty, alien phenomena that refract light in ways we haven't imagined. But the rainbows of Earth remain special and precious, products of conditions that, as far as we currently know, are still uncommon in the universe despite water's relative abundance. Teaching with rainbows. Rainbows are excellent teaching tools for science education, accessible phenomena that illustrate complex physics in visually engaging ways. Educators use them to introduce concepts like wavelength, frequency, refraction, reflection, interference, and the electromagnetic spectrum to students of all ages. Students can create their own rainbows with simple prisms, glasses of water placed in sunlight, or garden hoses on sunny days, making the learning experiential and hands-on rather than purely theoretical. The simplicity of generating a rainbow, requiring just light and water in the right configuration, contrasts beautifully with the depth of physics involved, offering multiple levels of understanding from basic observation to advanced mathematical calculations. Classroom experiments with rainbows often begin with prisms, triangular pieces of glass that refract light into its component colors. Isaac Newton used prisms to demonstrate that white light is composite rather than pure, and students recreate this foundational experiment centuries later, seeing for themselves how light separates into colors. Extending the lesson to rainbows in nature connects the controlled classroom experiment to the world outside, showing that the same principles apply universally. This connection between controlled experiments and natural phenomena reinforces the universality of physical laws and helps students understand that science describes the real world, not just laboratory conditions. Beyond physics, rainbows teach valuable skills in observation and patience. Finding a rainbow requires watching the sky carefully, recognizing weather patterns, understanding sun position, and being in the right place at the right time. These skills of attentiveness and pattern recognition are valuable far beyond science, applying to many areas of life. Rainbows encourage people to look up from their devices, to notice their surroundings, and to appreciate transient beauty that requires presence and awareness. In this way, they serve as gateways to broader engagement with the natural world, inviting curiosity that can lead in many fruitful directions. Rainbows and digital imaging. Modern cameras and sensors capture rainbows differently than human eyes perceive them. Camera sensors detect the same wavelengths of light that our eyes do, recording the intensity of red, green, and blue light at each point. But digital processing during and after capture can enhance or alter colors significantly, making rainbows appear more vivid or more subdued than they appear to direct human observation. Some photographers deliberately increase saturation in post-processing, creating images where the rainbow almost glows with unnatural intensity that catches attention but may not reflect the actual visual experience. Others aim for realism, trying to replicate the visual experience as closely as possible, which is more challenging than it might seem. The tension between artistic enhancement and accurate representation is ongoing in photography, with no single correct answer about what is right or best. Long exposure photography can reveal details invisible to the human eye in real-time observation, such as faint supernumerary arcs or subtle color gradations that our vision cannot resolve. By gathering light over seconds or even minutes, cameras accumulate photons that our eyes, seeing in real time, would miss entirely. This ability to see more than human vision offers both scientific value for researchers studying atmospheric optics and aesthetic opportunities for photographers, creating images that transcend ordinary perception, showing rainbows as they might exist to hypothetical creatures with more sensitive vision than ours. The proliferation of smartphones with decent cameras means more people photograph rainbows than ever before in history. Social media platforms fill with rainbow images during and after storms, creating a collective documentation of this shared phenomenon across the globe. This democratization of photography has created vast archives of rainbow images from virtually every location on Earth, each slightly different, each reflecting the specific conditions of its creation. These images serve as both data for scientists analyzing variations and as art, countless reminders of nature's beauty, captured, shared, and preserved digitally even as the original phenomenon faded from the sky moments after being photographed. Rainbows at night and rare atmospheric conditions. Beyond moonbows created by lunar illumination, other rare conditions can create rainbow-like phenomena at night or in unusual circumstances. Streetlights, stadium lights, or other artificial light sources shining through mist can produce partial arcs of color, though these are usually less vivid and less complete than natural rainbows. The artificial light must be bright and white, containing a relatively full spectrum rather than the narrow wavelengths of some lights, which limits the sources that can create these effects. Security lights, powerful searchlights, or bright stadium lighting might produce them under the right conditions, with sufficient mist, surprising observers who don't expect rainbows after dark or from artificial sources. Certain atmospheric phenomena resembling rainbows form through different mechanisms and can appear day or night. Light pillars are vertical shafts of light caused by ice crystals reflecting artificial light upward from cities or other sources. Halos are rings around the sun or moon created by ice crystals in high cirrus clouds, refracting light at specific angles. While not rainbows in the technical sense, these phenomena share the quality of making light visible and structured through interaction with atmospheric water in its various forms, whether liquid droplets or ice crystals. They remind us that the atmosphere is constantly transforming light through countless optical processes, creating beauty through physics. The night sky is generally inhospitable to rainbows because sunlight is absent by definition, but in high latitudes during summer months, the sun barely sets, hovering near or just below the horizon throughout the night in the phenomenon called midnight sun. In these Arctic and Antarctic regions during their respective summers, midnight rainbows become possible, created by the low-angle sun glowing just above or barely below the horizon even at midnight. These rainbows appear in perpetual twilight, neither fully day nor night, bridging two states, much like the rainbows themselves bridge earth and sky, water and light, creating beauty in liminal spaces and times. The sound of rainbows and multisensory experience Rainbows make no sound themselves, being purely optical phenomena without physical substance. But the conditions that create them are often accompanied by rich soundscapes. The patter of rain on leaves or pavement, the rumble of departing thunder fading into the distance, the rush of wind through wet trees, all accompany the visual experience of seeing a rainbow after a storm. In our memories, rainbows often come paired inseparably with these sounds, creating a multi-sensory impression that is richer than vision alone. The silence of the rainbow itself, its purely visual nature, contrasts beautifully with the auditory richness of the surrounding storm conditions, creating a sense of calm and peace emerging from chaos and noise. Near waterfalls, rainbows appear within the constant roar of falling water, sound so loud it becomes almost physical, vibrating through your body and making conversation difficult. In these settings, the rainbow is part of a complete sensory experience that includes not just sight and sound, but also touch from the kling with the present, cool spray, smell of wet rock and vegetation, even taste if you open your mouth to the mist. The rainbow seems to belong to the waterfall, inseparable from it in experience, though in truth they are separate phenomena, one optical and the other acoustic and mechanical. Their coincidence, creating associations in our minds that link rainbow sightings with specific sounds, smells, and physical sensations. Some people describe emotional or almost synesthetic feelings when seeing rainbows, internal responses that feel almost like hearing music or experiencing something beyond pure vision. While these are not literal sounds, they suggest that rainbows affect us on levels beyond the purely visual, triggering complex neurological and emotional responses. Whether through learned cultural associations or innate responses to color and light, rainbows touch something deep within us, creating reactions that feel symphonic and multi-layered, even though the phenomenon itself is silent, pure light, without sound, affecting us through vision but reaching beyond it into emotion and meaning. Conclusion: the eternal gift of rainbows. As we come to the close of our journey through the world of rainbows, we rest in the knowledge that these arcs of color are simultaneously simple and profound, ordinary and magical. They are light bending predictably through water according to unchanging physical laws, physics in action that we can calculate and predict. Yet they are also gifts of timing and beauty, moments that require no effort from us except to notice, to pause in our busy lives, and to look upward with attention and openness. Rainbows connect us to the natural world in immediate and powerful ways, reminding us that we live in an environment governed by elegant laws that sometimes produce breathtaking results, beauty emerging naturally from the mathematical structure of reality. Every rainbow is a promise, not necessarily of divine covenant or material treasure at its end, but of nature's fundamental consistency and generosity. The same physical rules that created rainbows in ancient skies, witnessed by our ancestors thousands of years ago, continue operating today without change, creating the same phenomenon across millennia. This constancy is deeply comforting in its own way. In a world of constant flux and uncertainty, where so much changes rapidly, rainbows remain dependable expressions of order and law. When conditions align in the familiar way, sun behind, rain ahead, proper angle, maintained, they appear faithfully and reliably, asking nothing except to be seen and appreciated. They teach us patience through their requirements, to wait for weather to clear and angles to align, and they teach us attention to recognize the precise moment when sun and rain coincide at the perfect angle. The next time you see rain falling while the sun shines behind you, perhaps after a summer afternoon thunderstorm or during a passing winter shower, turn away from the resigned sun toward the rain and look carefully for the arc. Let your eyes trace its curve gently from one horizon to the other, noting how red stands faithfully on the outside and violet on the inside, an order that has never changed and never will change regardless of time or place. Feel the cool air on your skin. Hear the rain's gentle rhythm or fierce drumming. Smell the petrichor of wet earth and allow yourself a full moment of pure appreciation without distraction. The rainbow before you is painted just for you by the chance arrangement of light and water and your vision, a collaboration requiring all three elements. It will fade soon, as all rainbows inevitably do, returning to ordinary sky and air. But while it lasts, it is a bridge between the world as it physically is and the world as we wish it to be, colorful, harmonious, beautiful, and full of wonder and possibility. As you settle into rest tonight, imagine yourself standing beneath a perfect rainbow, its arc spanning majestically from horizon to distant horizon across the entire width of the sky. Picture the colors glowing softly and purely, red fading seamlessly into orange, orange into yellow, a gradient so smooth it seems to flow like liquid light pouring across the heavens. See the landscape beneath it, rain-washed and gleaming, every surface reflecting tiny fragments of the spectrum, the world transformed by water and light. Feel the last drops of rain on your skin, cool and clean and refreshing, and the warmth of sunlight breaking through the clouds behind you, gentle on your back and shoulders. The storm has passed completely. The air is crystal clear and fresh, and before you stretches a ribbon of pure light that shouldn't exist according to our casual assumptions but does exist, defying the grayness of storm clouds with its insistent, joyful color. Let this peaceful image carry you gently into sleep, the rainbow arching protectively over you like a luminous canopy of hope. Know, with certainty, that somewhere on Earth, right at this very moment, a rainbow is forming. Rain is falling somewhere, sun is shining from behind the observer, and someone, perhaps a child or perhaps an elder, is pausing to look upward in wonder, their ordinary day suddenly transformed by 7 colors woven into an arc. Tomorrow, or next week, or next month, it might be you witnessing that moment of transformation. Tonight, rest deeply in the knowledge that the world contains such beauty, that physics and water and light conspire naturally to create moments of pure visual joy without any conscious intention. The rainbow does not know it is beautiful, yet it is profoundly so. And you, witnessing it, complete the circle of meaning, giving purpose to the purposeless, turning scattered light into lived wonder and remembered joy. Close your eyes now, breathe deeply and slowly, and let the colors of the rainbow glow gently and warmly behind your eyelids. Red for warmth and life, orange for energy and creativity, yellow for brightness and clarity, green for growth and renewal, blue for calm and peace, indigo for depth and introspection, violet for mystery and transformation. All the colors together, balanced and complete, a full spectrum of light and life and possibility. Drift now, peacefully and gently, into sleep, into stillness, into the soft darkness that welcomes dreams and rest. Rest easy, knowing that when you wake, rainbows will still be possible, still waiting patiently in the space between storm and sun, ready to appear whenever conditions align perfectly. Good night, and may your dreams be filled with color, beauty, and the quiet wonder of light transformed into meaning.